Hello. Okay, here we go. Here's the final exam thing. So what I'd like to show you here is this equation. So here's an example of a differential equation. Okay, let me get my pen out here. And so the thing to notice here is that we have this x times z in this system of equations. So this is a nonlinear differential equation. So, and notice here I have this lambda. This lambda is going to be a parameter. So I'm going to allow lambda to change. And we're going to take a look at what some of the trajectories of the solution curves look like for this system. Okay, so here's our initial value. So we're going to always have initial value x of 0 is 10, y of 0 is, yeah, 0 and z of 0 is 0. So let me pull up a little bit of my little software here, see what we got here. Okay, so what I'm going to do is I'm going to start out with this system. You can see it down here on the thing here. And I'm going to start with my time going just from 0 to 1 so we can see what's going on here. Okay. All right, so here we go. Let me get this system up here. There's our coordinate system. Okay, let me shrink it in here a little bit. Okay. I don't know if that's very good. Let me see. Oh, that's better. Okay, so here we have. Okay, that's really good. All right, so what we're looking at here is, just so you see, so this is the is three-dimensional space. This point right over here, that's our initial point, and we're using a this computer which has basically an integrating machine inside of it, so it can approximate the solution curves to this system of differential equations. And here we're looking, time goes from 0 to 1. So I'm going to increase the time, and you'll see a little bit more curve being added onto the tail here. Okay, so there we have it. So now what's going on here is that this trajectory starting off here is kind of wrapping around, and look at it's curling in there. It's curling in there. So if I get up to 100 here, you'll see it'll. Okay, so it gets a little closer. So apparently, it's approaching a fixed point, or of this system, or a steady state. So what I'm going to do is I'm going to increase the parameter here from 10 to 11, and we're just going to see what effect that has on the object. So not qualitatively, it's very similar. You see the trajectory goes wrapping around. It seems to limit out there. I'll increase that a little bit more. Up to 13. Gets a little. Looks like it's actually a good question is what is it doing? It looks like it's getting. See how seems like it's taking longer actually to get to that fixed point. Watch, I'll go up to 14. So what this indicates is that, yeah, see how it's taking longer? So this point is still attracting this orbit, we would say, but apparently the attraction isn't as strong, because you can see it's just taking longer to come in there. So I'm going to increase it a little bit more here to 15, that parameter. And oh, there, look, it's very slow. It's still wrapping around, still getting closer and closer, right? But now watch what happens here when we let's go on, just increase it a little bit more, 15.2, still going in there, 15.3, still doing it, a little weirder there, 15.7, oh, okay, so then some very unusual behavior occurs. So this is an example of some very complicated nonlinear dynamics, which comes from this very simple equation. I'm going to jack this up to more traditional values here. So here we have it. I think that's, so there it is. Oh, got a little larger. Okay. Watch, I'll keep increasing time here to 1,000, and it's generating it. So we get this very unusual figure being generated. I'll decrease that a little bit. And this is a very famous object in physics and mathematics. It comes from atmospheric science, called the Lorentz system. So this is the thing I wanted you to see. To solve this system is very difficult in some sense, and yet, so with the aid of the computer, we can see some of the finer structures. Now, what's happening? This is a very beautiful thing, actually. So I can make this smaller here so I can try to describe what's going on. So what part of the assignment now listed at the end is to look this thing up and just try to get some sense of what's going on. But essentially what's going on is if you follow the trajectories, if you look at this, let me stop it. It's hard to get it in right. What's happening is it's sort of, get a good picture here. Okay, they kind of, here we go. They kind of wrap around here, and they might wrap around, but then occasionally they might swing over here and then wrap around here a few times and wrap around here and around here and then go back this way. This is an object of intense study early in the in the 1990s. I spent a lot of time studying this object along with a lot of other people in mathematics, and many beautiful theorems were proved about this object. For example, there's a collection of knots called prime knots in mathematics, and they all occur as orbits in this system. In fact, you notice how we started here at this point here. Well, this is a differential equation. So what happens is that this orbit that you're looking at here is a unique orbit. So for it to be periodic, it would have to come back and actually meet at its original spot, and it doesn't. So okay, so that's enough of that. I just wanted to see, everyone should see the Lorentz attractor. So here's your official assignment for your final exam. Just answer the following question, really goofy question, it's pretty obvious. Do you think that the orbit of this 1000 is periodic? And that would be for, you can look at the video here. That's for, let's say, lambda equals 17, or whichever one I had shown you at the end there. Now, then what you should do to just get a sense of how in depth the study of this object is, just do a Google search on Lorentz system, and you'll see an enormous amount of information on it. So then other than that, just finish up your final, hand her in, and I hope you've enjoyed this semester. If you have any questions, please feel free to get a hold of me. Thanks. Bye.